So, gentlemen, thank you so much for joining us. We're all eager to hear your wisdom and highlights on the chiplets area. First, let me allow each of you to briefly introduce yourselves and tell us a little bit about your company and your company's interest in RISC-V and chiplets in particular.
Thank you, Calista, for having us all here. Thanks to the overall ecosystem for showing up. My name is Aniket Saha. I'm responsible for IP products at Tenstorrent. I joined Tenstorrent about 6 months ago because I saw the massive uprising in RISC-V all over the world. And it is great to see a lot of new products come over. At Tenstorrent, we are focused on delivering and accelerating AI everywhere. RISC-V is a critical technology which enables that. We are building open source technology-based platforms with our friends and the overall ecosystem because we believe in creating an overall ecosystem, an open ecosystem based on open source technologies, which can enable AI and the development and acceleration and application of it everywhere. We are playing in various different markets right now. We are working on machine learning, AI, automotive, HPC, and we are seeing RISC-V as well as our products go into markets which we did not imagine about last year or year before. Completely new markets are opening up. And without RISC-V, a lot of these things would not have been possible. So we are truly indebted to RISC-V for enabling some of these technologies to come to fruition. We are launching our chiplet-based products next year. And chiplets combined with RISC-V is truly a game changer. We'll talk more about it in the next couple of minutes, but let's see what our other panelists have to say.
Thank you.
So I'm Dale Greenley. I'm at Ventana Microsystems. Thank you, Calista, for having us. You heard Balaji talk yesterday. We've been in the RISC-V world since late 2018. That's when we were founded. Employee number 1 joined in early 2019. Our charter from the beginning was to build the highest performing RISC-V processor we could conceive of. I think we've done that. The reason we got into RISC-V was we saw the opportunity that other vendors weren't providing. The x86s and the ARMs, they were going a slightly different direction, not as open, not as inclusive, not really allowing folks to customize what they were doing and add value. So we are thrilled to be part of the ecosystem. We're glad that sort of every available market out there is being attacked by RISC-V vendors, whether they're hardware vendors, software vendors, whatever. And we think at this point, we want to see everybody succeed because if everybody succeeds, then RISC-V succeeds. And if RISC-V succeeds, then I think the world's a better place.
So like when RISC-V succeeds?
There you go.
I think it's already succeeded.
All right.
RISC-V is here. I heard that recently.
Thank you.
Hi, Laurent Moll. I'm from Arteris. I've been at Arteris for quite a bit, more than a decade actually, and through the acquisition at Qualcomm, also worked at Qualcomm for many years. So I've been on kind of both sides of the coin as an IP provider and also as a frantic user of a lot of technology to make a lot of chips. Arteris has a very special place in the RISC-V ecosystem because Arteris is really a neutral company. We're trying to make sure that anybody who needs to build an SoC can use our products. What we bring to the table is enable a lot of the SoC vendors actually to basically pick the solution they want. And that would include a lot of the RISC-V IP vendors and potentially the RISC-V chiplet vendors and make sure they can build SoCs with this. So we have direct partnership with a lot of RISC-V vendors. We have a lot of customers who are building RISC-V. And our goal here is to make sure that we both help everybody make chips, make sure that we help them unify how they're building their flows and everything, regardless of which type of RISC-V they're using, and also trying to lower the risk for everybody of using something new from a new vendor who hasn't been established, and we kind of help people use that, that particular vendor and make sure that their system will be successful. It's really, and the Arteris has been successful because people have been making extremely complex chips and need to connect hundreds of different IPs. And so the influx of IP vendors who make RISC-V CPUs and chiplet vendors who make RISC-V chiplet is kind of adding to this complexity of, I've kind of picked what I want, this really works for me. Now how do I make a chip out of it? Or how do I make a chiplet that connects to it? Or how do I make a system that connects all of these chiplets? So this is kind of where we're playing. And even though we're not directly providing any RISC-V related IP, we are working with the whole RISC-V ecosystem and are kind of very excited to see all these new players coming in and adding to the and kind of building up the ecosystem.
Very good. I'm Rob Aitken. I've been at Synopsys for 18 or so months, and prior to that was at ARM for a long time. And I'm taking a quick poll. How many people out here worked at ARM at some point in their careers? Yeah, okay. Synopsys has an interesting presence in RISC-V universe, and as of yesterday, it's different than it was in that we announced the ARC-V cores, and so Synopsys now sells RISC-V processors. Come and talk to us. But in addition to that, in the kind of the ecosystem play, Synopsys supports the SoC ecosystem at multiple levels. So we provide IP like processors, but also standard cells, I/O, and connectivity, and so on. We provide emulation, we do tools. And from a chiplet angle, I think it's kind of interesting because when you actually go to the challenge of I'm going to build a chiplet or I'm going to sell a chiplet or what have you, the EDA interface to that and the IP interface to that is really critical. So that's something that we've been spending an awful lot of time thinking about how that works. We've got various approaches that we think help that. But altogether, this is all part of the ecosystem that's developing around RISC-V and in general. So happy to be on the panel.
Thank you so much. So we've got a collective wealth of experience here, and it is sort of a small world as we start to run into various threads from working at ARM, Intel, IBM, all the others as our world kind of converges and that collaboration spirit. It's easy when you've got friends in all places, right? Yep. So thank you for all of those great intros. I wanted to start a question with Dale. What, if anything, is unique about the value proposition of RISC-V and chiplets? Why are some companies that might otherwise have a pure processor IP business model productizing their technology as chiplets?
Those are two big questions. So
we can take them one at a time.
Take the one at a time and maybe remind me of the second one if I forget. So the way I look at chiplets and RISC-V is that really there's nothing specific about RISC-V, why that's a value proposition that the RISC-V folks should embrace versus anybody else. I think you can look at products from the x86 folks, recent announcements from ARM. There are many people who are doing chiplet-based implementations and systems. So from that perspective, I think what you see is the market kind of dictates times when you want to do monolithic SoCs and times when you might want to do chiplet-based SoCs. So for us, aiming to be in this high-performance space, wanting to do small core count designs all the way up to like 192 core count systems that we announced with V2, we know that the low-end things are going to probably be monolithics, and the high-end things, unless you want to do wafer scale integration, you're either talking about multiple monolithics or you're talking about chiplets. And for us, from a performance perspective, from a kind of a customer perspective, it made sense to kind of approach this from a chiplet perspective, and to go that direction. That's something that we looked at initially. That was kind of a focus for the company. We validated that with a number of customers, a number of investors, like Cisco, who was our initial investor. So we see the value in chiplets because that's something that we can do. But other people see it too. So depending on where you are in terms of what sort of product you're trying to build, chiplets may be for you and they may not be for you.
So it sounds like as a business, you're taking end user in mind and what is the best, kind of application for the challenge that they're wishing to meet.
Right. I mean, we didn't take the approach of let's build a chiplet and they will come. That wasn't what we did. And if you're going to be in business, you need to do what the customer is wanting to do and what they're willing to pay you to do. And so the customers, what they saw was whether they worked in the x86 world or they worked in the ARM world, they were under some level of constraints that they didn't want to be in, whether that was lack of choice, whether that was lack of extensibility, lack of openness, and the ability to kind of add value to the systems.
So I think, a lot of us are out here are business stakeholders in one way or another. Are there businesses that would then take just a monolithic approach or just, composing IP into their own designs versus just taking a chiplets approach? I mean, it sort of gets into the next question of the pure play of the business model. Like, how would you guide or suggest direction to those companies who may be making those decisions?
I mean, I think, it's how broad of a market space are you aiming at? If you're aiming at, let's say you wanted to do wearables, kind of a la what the Qualcomm folks announced yesterday, if that was the only thing you did, you're probably not going to do chiplets. Your performance requirements are probably not high enough. You don't necessarily, get the advantages out of chiplets that you would when you do a big system. If you were doing kind of big iron sort of approaches, then chiplets are probably for you. You see the IBMs, the Intels, the AMDs doing chiplet-based systems. If you want to cover all of that, then you probably do a mix of both.
So it depends on where you're aiming your business, and one end or another fits or better or worse.
That's my belief, yeah. So, and that's why we provide both IP and chiplets, because we think there's certainly room for both.
Yeah, well, at some level, RISC-V itself is a very modular ISA, as you can pick and choose those extensions that fit, and then when you get to the chiplets level, it becomes even more composable from there. So others would like to weigh in on this?
Yes, one of the things I personally believe is if you're targeting a broad-based market where you have very different requirements, chiplets and RISC-V are almost complementary technologies there. RISC-V is extensible, as you're mentioning, right? So you can customize it and tailor it to the specific market you want to. But the base requirements often don't change. The compute requirements is almost the same. So you can have a compute die, which is doing all your compute, and then you have an accelerator die, which adds in the specialization that you need for networking or servers. So if you have a broad market, like Dale is mentioning, chiplets is a great play. Combined with RISC-V, it enables you extension, acceleration, customization. But if you're playing just in one market, you don't have to do SKU management. You don't have to have multiple products. Monolithic might still be the play there. And of course, your power, performance, area requirements. Doing chiplets is not cheap. It takes a lot of effort to break down a monolithic die. And if you're going to be in a market which the market window is not long enough, maybe it's not worth your time, or maybe it is. That's something we need to do the business analysis to figure it out. But chiplets and RISC-V together just gives you a lot of flexibility to run a business. And a business manager, my background back in the day, I used to run chip design teams, et cetera. So I wish I had chiplets and RISC-V back then, because building a portfolio of products becomes a lot easier. Obviously, the upfront investment is there. You need to put in the work. There is no free lunch. But once you have invested in there, you can come up with new products very quickly, because you have to change portions of it only.
So, Laurent, Aniket just talked about, hey, it's a little bit more complex to do chiplets. Can you speak a little bit to the complexities and some of the decision-making that you're seeing in taking one approach over another?
Yeah, absolutely. And I was just thinking, we all agree that chiplet is all about the business side of it. But there's really two different aspects to this. One, the most obvious one is maybe the production cost of chiplets, where you have a large die, you cut it in parts, your yields goes up, et cetera, et cetera. And certainly if you're in a high volume business, you can crunch those numbers, and this is probably what's going to direct if you're going to make chiplets or not. However, there's NRE is an extremely important aspect as well, because not everybody is making 100 million parts of something, and actually building the things, then the cost of chiplet has to be considered, and so that's most people. I guess the example earlier about Intel and AMD, they're in a corner of the high volume market. Most people are not there, and they have to consider chiplet in terms of how is it that's going to change their NRE, and it can change in both ways. It can be very positive. For instance, looking at Ventana, having a CPU chiplet means that you don't have to be in a super high high performance node, that you don't have to do physical design on a multi-gigahertz processor. All these things are incredibly expensive. On the other hand, you have to deal with all the complexity of the chiplet. So you have to deal with more vendors, because suddenly you have 5 vendors, you have more silicon and packaging vendors. Your supply chain gets more complicated, so again, it's more engineering time trying to figure it out, all the new protocols and everything. And so that aspect, certainly from our side of the business, where we deal with complexity for our customers, this is the thing that's the most important, because we're trying to enable people to make chiplets out of anything, including RISC-V CPUs, and certainly RISC-V chiplets are something that's that's kind of up and coming, and a lot of people are looking at that. But how you deal with this complexity, how do you enable vendors to either make a chiplet that connects to RISC-V chiplets, or make a whole system that's comprised of multiple parts that they are building internally? This is very important. So complexity management with chiplet, it used to be complicated to make an SoC. Making a system out of chiplets is a whole order of magnitude more complex. And so there's a lot of work for everybody to do to reduce that complexity. And part of RISC-V International is actually trying to help standardize, and we'll talk about it later. But standardization is at the core of enabling people to use all these new technologies.
Rob, any comments?
Yeah, I agree with all that. There's another angle that we have touched on. I think Laurent touched on it briefly, on heterogeneous systems, and that's one where we see a lot of demand from people who don't make 100 million parts, but at the same time have things that just work better on different technologies. So if you have a CPU die that wants to live in digital CMOS and an RF die that really doesn't, then a chiplet-based solution is an excellent way to go. There's a complexity, as Laurent was alluding to, there's an entire layer of complexity around how do I put all this stuff together? How do I get it to yield? What does it mean to sign this off? And all kinds of nitty-gritty implementation stuff that comes in. But there's also potentially the opportunity to create something like what Ventana is doing, of saying, this is your CPU subsystem. You don't have to worry about it. It just is here. And incorporating that into a design potentially opens up new markets for people to play in. So there's a lot of potential with chiplets. There's a lot of necessity to figure out what your system looks like do design exploration up front and say, I've got a software problem. How do I determine which goes where? Should I have an accelerator or shouldn't I have an accelerator? These kind of questions. But again, the existence of chiplets and the standardization of RISC-V helps to simplify that process a little bit, I think.
A lot of variables. A lot of variables go into any architecture discussion, much less form factors, right? So moving on to Aniket, there are a lot of domains and areas where we're already, kind of surfacing where chiplets approach makes more sense. High performance, higher end stuff, we see a lot of utility there. But what about other domains? I mean, where are we at in things like automotive or other applications?
Very good question there. The main areas where I'm seeing chiplets make sense is HPC data center area, where the dies are big and you need to do very specialized functions. The workloads are changing really fast. So that requirement for differentiation and coming up with a new SoC quickly is coming up. But the market which has been most surprising to me is automotive, because automotive tends to be very conservative, very long life cycles. They don't want to change things. But over the last 3 years, something has changed in the automotive world, and they have become the most aggressive adopter of new technologies. If you go back, see who's investing us, Hyundai made a massive investment in Tenstorrent. They believe in our chiplet strategy, our architectures that we are bringing to market. And when I look into what the automotive world is requiring right now, the main thing they want is scalable platforms, which can scale from low-end cars to very high-end cars. They don't, and while maintaining the total cost of ownership of software. They want to build once, deploy everywhere. And how do you deploy the same silicon in multiple places? Chiplets. You add multiple different dies, get you the same sort of additional compute if you are going from level 2 to level 5. You can add various different compute dies with various different I/O dies and the accelerators that are required. In the data center space, one of the things we're noticing is people are doing accelerated compute or offloading compute from the CPUs. And there again, they're like, okay, the workload is changing really fast. We don't want to change the entire system. We just want to change the portion of the workload we want to accelerate. So the accelerator is a great example for chiplets. The compute die stays the same. But it's not very easy, right? As Rob is mentioning, there's a lot of additional complexity there. In automotive, one of the biggest challenges is no one has really considered functional safety for chiplets. That while we have in the IP world tackled functional safety as safety element out of context for IP for a long time now, and it's well understood, chiplets is a completely new thing for us. I'm sure the whole industry is working on it right now. There's a lot of RISC-V is actually helping there. There's a lot of other consortiums that are being formed to understand what does functional safety in the chiplet context mean. ISO 26260 board is also looking into that in quite detail. So we will solve this. And the good thing is there's so many bright, intelligent people working on this problem because it's an open source ecosystem problem that we are coming to solutions much faster than when we worked in proprietary ecosystems.
Excellent. Other domains that anyone would like to offer as
Aerospace is another one that's
aerospace?
very interested in this stuff, and for a couple of reasons. Number one is, again, they have this disparate technology that they're trying to, but the other one is, in a lot of airplanes, there's a fixed space that was made for compute a long time ago, and if you want to do more compute and plug it into that same space, chiplets is an excellent way to reduce volume, basically, and be able to fit more stuff in a smaller space. And if you design it right, it's a way to maintain the power. You know, and if you fail to design it right, then it's a challenge. But doing the work and figuring out how am I going to fit this extra compute functionality into this smaller space at the same power is something that they care about a lot.
Do you also see the same growing thirst for new technology as we've heard about in automotive happening in aerospace?
It's similar, and it's different in the sense that, you know, in their ideal world, they'd like to use something that somebody else has used for 20 years and it's worked fine. But the ideal world no longer exists, and they're forced to look at more innovative processes and trying to again combine these multiple systems, especially RF radar type systems, with digital processing. And if you can combine those in a way that allows you to get past some of the classic interconnect bottlenecks, that's something they're very interested in.
That's a great point. We see in the automotive space as well, like the analog portion is not changing because they don't need to move to the next new hot node, right? So they stay on the older nodes, put it on a chiplet, which does the interfaces, let the compute die change. So yeah, we're seeing that in various different markets.
And for us, I think we see the same thing that you see at Tenstorrent. You know, we see folks in the automotive space very interested in chiplets, and folks who want to mix and match functions to do kind of the domain-specific acceleration where they can build systems that they couldn't build before because they couldn't reach inside of the system. They got some monolithic thing that was an SoC, and they couldn't, you know, get inside and get close enough to sort of, you know, get the same level of performance or interconnectivity that they would once you've sort of torn apart that SoC.
And following up on what Aniket was saying about automotive, I think the big automotive manufacturers now, and the tier one for a while, they're kind of the ultimate catalog shoppers. They really want this and that and that and that, and be able to not go for one brand for too long. And I think they've been trying to do this for a long time, and it's been not super successful because of integration costs and all of these things. With Chiplet, they're certainly pushing very hard because they're seeing this as kind of the solution. Of course, the solution is not easy again because all of the integration problems, especially multi-vendor integration, which we're very far from.
Yes.
But they really see this as something they have to do. Be able to pick the best in AI, the best in vision, the best in infotainment, the best in radars and other things. And for them, this is the holy grail. How do I not invest in making these incredibly expensive chips while still having a system that meets my requirement? So there's definitely a lot of enthusiasm, and there's a number of RISC-V companies that are well placed in that domain because they bring existing chiplet businesses, or they bring a lot of knowledge. Some of them actually with automotive background. So there's and there's not a lot of other options really than RISC-V on the open market.
Thanks, Laurent. So, we talk about just the hardware and the IP pieces getting along. This brings us to the next level, right? So, Rob, tell us a little bit about how do you get the software, the ecosystem that we all depend on around that to run seamlessly in this now new chiplets approach.
That is always the big challenge, right? And because Chiplet spans many things, there are many answers to that. So in terms of a chiplet that performs a particular function, if you can make that function specific enough, then you can develop its own little software ecosystem. It's effectively an embedded object, and you can use pretty standard tool sets to make all that go. Like, we have similar tools and so on. But I think that where it gets more interesting in chiplet space is actually when you're trying to combine multiple chiplets from multiple vendors into something. So if you are building a giant system and you've split it up into a dozen chiplets, and you as a company or an entity are building all of them, then you still have a giant software problem, but at least it's a manageable software problem and you kind of control all the bits of it. But the automotive catalog shopping part, that is a different beast altogether, and that's one where the standardization of instruction sets, the standardization of interfaces, the standardization of everything really, really, really is a key component to making that go. Because without that, it's just never going to work. It would be nice if all of the RISC-V software ecosystem problems were solved right this minute, but they aren't quite, but they're getting there. And that's, I think, that's a thing, again, where the vector is going in the right direction. So getting these platform definitions down so that the software has something to talk to is really, I think, a key part of making that go forward.
Having the RISC-V profiles being standardized has been very important for that, right? Yes. Because before that, we were all building our own little versions. But now automotive vendors and other customers will say, build RVA23. Do not add extra stuff to it because you feel like it. Put it in your accelerator. But I want all my software to be compliant to RVA23 profile processors.
Or if you do add it, I'm not going to use it.
Yes, well, that's there too, right? So in the interests of running a business, we are listening, right?
Right.
We're not trying to add artificial differentiation, but randomly.
But sometimes, they don't even want you to add it because someone might accidentally use it and then suddenly you have an incompatibility.
Exactly. And if you look at the automotive software stacks that have developed, pretty much everything is supporting RISC-V, and it happened over a bunch of maybe 5 years. It took ARM almost 12, 15 years to get there. So I think RISC-V's standardization took really long.
So I do agree, we're on a much faster trajectory, but part of that is that we've learned from history, right?
Exactly.
We've learned from what else is going on in the industry. We're all in the same kind of family here, right? We've got these experiences that we draw that are able to help us accelerate that path.
Yeah, absolutely. I mean, even if you look at ARM 15 years ago, there were differences in implementation of cores in different places, and it was a software nightmare. And
Yeah.
There were different architectural partners who had different products, right?
Yep.
But the standardization is definitely helping. And I'm really liking the fact that all vendors are starting to follow the standardization process. And they've stopped trying to do their own thing.
I think it helps the end user. It also helps the vendor be, more amenable to different customers, to be able to be, that you don't want to be locked into any one vendor, and that's a two-way street.
Yep. You don't want to create a software lock for your vendor. Yeah, as much as you want to, that will actually, you will end up not being adopted. If
It's
you
a
do
short-term strategy,
Yeah.
very short. All right. So we've talked about, the hardware, the software, but there's still that connection point between chiplets, between on-chip and some of the interconnected communication technologies. Laurent, do you want to speak a little bit to some of the key advancements, requirements that we need in that space?
Sure. Really, kind of building this whole stack from hardware to software is incredibly complex. And with people doing shopping of chiplets, especially heterogeneous chiplets made by different people, it is incredibly complex at all levels. And so, in the context of RISC-V is kind of interesting because RISC-V is all about freedom to innovate. Although because they're customers, there's some amount of standardization that needs to happen for it to be successful. I think that what we're seeing on our side of the ecosystem is that. How things connect to each other. Standardization is absolutely critical, and we always prefer to see existing standards being used because they're tried and true. They all come with their existing ecosystems. Tools are available, and so as much as on die, even though it's a little bit of the wild west, even though there are kind of existing standards that everybody uses. Chiplets is a whole other level because you have, the PHYs with different vendors. There are, sometimes interoperable, sometimes not. There are multiple levels of the PHY of protocols on the PHY. UCIe is a good example where, there's a lot of enthusiasm for UCIe right now. But there's multiple levels at which you can intercept the stack. There's multiple vendors that have different offerings, and so people who want to connect to it, they have many options, which is good. But when you're trying to manage complexity, it's not as good. So our recommendations, and we work with a lot of RISC-V CPU vendors, both on die and on the chiplet side. We've actually had an announcement with on ARC-V yesterday, and also with Sci-Fi, Semidynamics, and most others. And our recommendation is always, this is not a battle for today. It's a battle for tomorrow, maybe, to try to find better options of connectivity on die. Let's use tried and true methods, because right now this is not the place where any of you is going to be able to differentiate. So a lot of our partnership is making sure that we can actually connect everything, and that when the customer shows up and says, I want to connect this and this and this, we can say sure, because we've actually talked to all these people and we know that we can do this. At the chiplet level, again, is much more complex. There's the PHY and the controller stacks that are in the middle, and again, there's a lot of different offerings there. And for us, it's for most people want solutions, and so solutions usually are trying to use things that are as standard as industry, or either actual standards or industry standard as possible, so that they don't have to reinvent the wheel. Because again, chiplets is not something where the economics may make sense, or again, the NRE may make sense to do chiplets, but all the investment that's necessary, this is kind of sunken cost, and you have to deal with it. And so the easiest it is, the better. So partnering, again, across all of the RISC-V ecosystem, making sure that the pace of innovation is in the right place, making sure that we standardize things that need to be standardized. All the system components, for instance, it's important that they're kind of the same so that people understand how to put an MMU or an interrupt controller or these things together so that all the systems support the same software and can be assembled. But in the places where RISC-V connects to the rest of the world, I think the most important thing actually is to try to be standard with things that are outside of RISC-V, where big industry forces are kind of making changes and that are really not related to RISC-V. UCIe being a good example. UCIe is kind of different. It's done somewhere else. It's pushed by people that are definitely not RISC-V. But if the economics of scale makes sense, if the ecosystem is there, then use that. Then later we can solve that problem. But for now, standardization, 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 because complexity is just growing with chiplets.
And maybe I'd add one thing onto what Laurent said about UCIe. So our first generation V1 was a chiplet-based product. It wasn't UCIe. UCIe wasn't available, wasn't standard at that point. So that's a case where the lack of that standard, has kind of gotten in the way a little bit. So our second generation now is going to be a UCIe-based PHY. We provide a link layer around it, but that standardization is important. And soon, hopefully soon, the various PHY vendors, they'll be able to interoperate. I don't think they're quite there yet. So at least initially, you're going to have to, if it's a Synopsys PHY, it's going to have to talk to a Synopsys PHY. Over time, we want a Synopsys PHY to talk to a whoever PHY, a Blue Cheetah PHY or a Cadence PHY or whoever is making that PHY. And then going back to, in terms of, for example, either on-chip interconnects or chiplet-aware interconnects, stuff that, Arteris is kind of in the middle of, that's key to us. We want to make sure that we can fit into that ecosystem. We want to make sure that the people that we work with, people who do hub designs that we would attach our chiplets to, that we're speaking the same language that they're speaking.
So, Dale, dive a little bit more into kind of the nuances between designing an SoC versus taking a chiplet approach. Like, what are some of the challenges and differences that you're seeing off the top in the tools and other resources that you need? What are the challenges?
I mean, I think it's certainly another layer of hierarchy that if you were doing a monolithic, you might not, at least a chip designer, you wouldn't care about. In this case, you need to do a different level of partitioning. Now, everybody does partitioning within an SoC, but the considerations may be a little bit different. If you want to communicate via chiplets, you're probably using a common link layer. You're doing something maybe to tunnel a protocol or a set of wires across. On an SoC, you don't think about that. You have you want to talk to functional unit A, you send some data, you send some control, and off you go. And you don't really think about how do I make that communication as efficient as possible? How do I make it, it's a wire. It's not. I don't have to worry about latency. I don't have to worry about going back and forth across the chiplet boundary. Obviously, if you're hooking up a system that's made of multiple chiplets versus an SoC, now you're having to deal with hooking those things up on a substrate or using interposers, and so you're doing kind of that PCB kind of level thinking about connecting things together. How long are my trace lengths? Am I creating transmission lines that I really don't want to deal with, or am I keeping things short enough where I can, kind of treat it like regular wires? And then power distribution and clocking, all those things are a little bit different when you're dealing with chiplets.
There's no reference design flow. That's one of the problems, right? Because you're learning as you're building the chiplet now. Like with SoCs, it was almost like you could go to a standard EDA vendor, Synopsys, Cadence, Ansys, Mentor, and they have reference design flows. But for chiplets, there are now, but it's still not standardized. You still see problems which you are like, oh, this is for the first time I'm seeing this problem in this new node. So it's not just a node problem. It's on top, there's a new layer of hierarchy.
I think, some of that is a standardization issue in that we can conjure up a chiplet design flow, but if you're building chiplets a different way and connecting them into a system differently, it's sort of pointless. So there's effectively, over the next few years, I think there's going to be settling down on the ways of doing things so that if there are multiple ways of doing something, we all collectively just pick one so that we don't have to, create n squared different chiplet interfaces for n chiplets.
Yeah, the mix and match dream is great, but to realize it is very difficult. You have to constrain the options.
You very much do, and you have to not just constrain the options at design time, you have to constrain them at manufacturing time so that you have an electrical, physical object that connects into your system in a predictable way. So yeah, the idea of I'm just gonna swap out this for that is a long way away. I mean, even now I've got a PC and I bought new memory for it, and it said, oh, your new memory, which is a DIMM, which follows, you know, LP, DDR, whatever, is incompatible with this motherboard, even though it's allegedly the standard. And this is something that's been around for who knows how long.
I love that idea. We're going to agree on a way of doing things.
Yep.
We're on it.
As long as you pick my way.
Yeah, I was. I didn't want to go to the rest of that sentence, but yeah, you know. So whose way are we picking this time, right? So let's start at the far end, Rob, and we're going to come down the line. Where do you see chiplets? 3 years, 5 years?
Chiplets, I think 3 years from now, I think we will be close to this standardization concept, in that, you know, a chiplet you can buy 3 years from now is in somebody's head being designed now. So that standardization process will continue. It will also become increasingly obvious what the costs of doing this stuff wrong are. So that's something that I think will you know, as more people try it and say, well, that's not quite what I wanted, then we'll get more standardization. So 5 years from now, we will be well into the glorious future, and everything will be all solved. And if you believe that, I have some investments I'd like to talk to you about all afterwards. But yeah, we're definitely, I think, going to be further along. And again, going back to the sort of the non-chiplet premise of the panel, I think RISC-V is going to be a key driver for that, precisely because the ability of different vendors to create RISC-V systems and for them all to work together at a software level is something that's going to really help the chiplet ecosystem.
Thank you. Laurent?
I mostly agree with Rob. I think Rob is particularly optimistic today, but
I'm very optimistic right this minute. Yeah.
What we're seeing right now is the people who are successful with chiplets are people making very large, not necessarily homogeneous, but chiplets made by the same company, you know, using, you know, the same teams and people who understand what they're doing. And so that exists, that's successful, and that'll continue being there. The next step is people within the same company splitting their chips into multiple parts, either for scaling or for yield or for other reasons. And I think that's certainly things that we're going to see more prevalent in the next, say, 3 years. The next after that is, you know, the next step is things, you know, the way that Dale was mentioning for Ventana of trying to go from a kind of proprietary interface, because, well, that's all there is, to a more, you know, standard interface. I think after that, we're going to start seeing this appear, like multi-vendor systems that actually, you know, working well. And then, you know, the whole ecosystem of doing catalog shopping and connecting things, yeah.
It's a ways out.
Yeah, it's going to be complicated. It really is going to be depending on the success of some of the, you know, more forceful drivers for this, including the automotive manufacturers and tier ones, because they really want it to happen, and, you know, we'll see how successful that's going to be. But it's going to be by far the hardest. I think the industry, you know, we're talking about, you know, Aniket was talking about SoCs being kind of an understood problem. Even though it's a complex problem, it's understood. You know, it took, what, 20 years to get there? You know, I was making some of the first multi-core CPUs back in the late 90s, early 2000s, and, you know, now only we understand how to do this properly, what the tool chains look like, you know, how to pick IP vendors and things like this. So chiplets is, I'm not, you know, it's not 20 years, certainly. But it's going to take some time. It's going to take a lot of industry efforts from everybody to find ways of doing this, the flows, the software, the products, you know, at every level to get there.
All right, Rob?
I think we're in the, maybe we're not even at the early adopter phase. Maybe we're pre-early adopter phase. So I think in 3 to 5 years, you're going to see an acceleration of people doing chiplets. But I think people are going to need to see how to do it. They're going to see some successful proof points. Certainly stuff that maybe one company is doing, that'll set the standard, and then over time, the heterogeneous stuff I think will probably take a little bit longer. But I think, again, if the value proposition is there, that the market I'm attacking, the economics, what I save in design time, what I save maybe reducing risk, what I don't have to do, I don't have to, there's parts of my system I don't have to, fab again or go back into the, pay $13 million to do a tape out, then I'm sort of happy about that. And if I start seeing that working, then I'm more likely to adopt it. And when we have tools and stuff that make that easier for everybody else, then I think you see more people jumping in.
Fantastic. Aniket, last thoughts. Bring us home.
3 to 5 years, right? The first wave of innovation in chiplets will basically be in the data center space. Yep. And it will be the single vendors who are building the whole system. They're breaking it up into chiplets. 5 years plus, that's where I see the heterogeneous multi-vendor chiplets coming to fruition. Looking at RFIs right now at 2028, 2030, I see automotive guys talking about chiplets in automotive space. So I think 5 years plus, we will start seeing automotive SoCs. So that will be the next market which moves to chiplets. But I sort of agree with what Dale is mentioning here. The first wave is going to be single vendor, and then it will slowly move.
But I think that single vendor data center is going to give us the volumes that are going to give credibility to the next wave. So.
Absolutely, and they'll keep all of us gainfully employed.
Hey, everybody likes a paycheck.
Exactly.
All right. Well, thank you to the panelists. Let's give them a round of applause.